Thank you. Thank you very much. Good morning. Welcome all of you to the open channel flow. And we are now in the fifth module of the open channel flow. In the previous classes, we have seen about the simple definition of the open channel and various types of open channels and the comparison of open channel flow with the biflows. Then the classification of flows like steady, unsteady, uniform, non-uniform flows, laminar, turbulent flows, then critical, subcritical, and supercritical flows, and this classification based on different criteria. And then we looked at the distribution of the velocity for different shaped channel sections. Correspondingly, the energy and momentum correction factors, their expression for alpha and beta, and the derivations have been taken up. Yesterday's class, we started about the uniform flow, and we noticed that the uniform flow occurs in a prismatic channel, and the governing formulae for analyzing the uniform flow in open channels are like Chezy's formula, Manning's formula, Basin's formula, Ganglet Cutter's formula, and then Darcy-Weisbach friction factor equations. So we have seen about the various formula which may be used. Among all these, also the Manning's and Chezy's formula are more and more used. And even in Manning's formula also, the Manning's coefficient n is a governing parameter because the Manning's formula is given to be the velocity v, the mean velocity v at any given section in open channel flow will be equal to 1 by n, r to the power 2/3 s power half. S is the longitudinal slope and r is the hydraulic radius. N is the Manning's coefficient, which depends on various parameters like shape, size, flow conditions, and then resistance to the bed and the sides of the channel section, etc. And we discussed about 10 parameters on which the Manning's coefficient depends, and all these parameters also are interdependent, and Cohen developed one equation for finding the value of n that we have seen. So in today's class, application of the Chezy's formula and application of the Manning's formula for analyzing the uniform flow, we try to work out some of the numerical problems related to the uniform flow using Chezy's and Manning's formula. So problems on uniform flow. Let us see some of the problems. Some problems are similar in nature, but still we try to work out as many number of problems as possible in today's class. The idea is that you should get practice, and secondly, and the problems are different varieties. Like in some problem we may calculate the longitudinal slope, in another problem we may calculate the velocity, in another problem we may calculate the side slope, and so on. The governing equations are same, the Manning's equation and Chezy's. These are the two things that we use. So we start with a very simple problem for analyzing the uniform flow in a rectangular channel. So a rectangular channel, 2.5 meters wide. The width of the channel is given to be 2.5 meters. Bed width is given 2.5 meters. What would be the top width? The top width also would be equal to 2.5 because it is a rectangular channel. Since it is a rectangular channel, the bed width and top width are same. So the width is given to be 2.5 meters and carries water at a depth of 1.2 meters. That means the depth of flow y is given to be 1.2 meters. The bed slope of the channel is 0.0036. Calculate the average shear stress on the boundary of these channels. A rectangular channel with bed width b, the depth of flow y. So the average shear stress tau naught is given to be gamma r into S naught. S naught is the longitudinal slope. Sometimes we are using capital S as the longitudinal slope. Sometimes we are using S naught as the longitudinal slope. As far as the uniform flow is concerned, both are same. S naught otherwise would be equal to the slope of the channel bed. Slope of the channel bed. If the flow is non-uniform, that would be different from the slope of the water surface. Also would be different from the slope of the total energy line. But since we are considering the analysis of the uniform flow, all are equal. So sometimes we are using S naught, or sometimes we are using only capital S. Both mean the same. There is no difference. So gamma, the specific weight of water, and R is the hydraulic radius. So you need to calculate the hydraulic radius for this. The remaining two parameters are known. S naught, the longitudinal slope, given in the problem 0.0036. Gamma, unit weight of water, 9810 Newton per meter cube. These two are known. So R, the hydraulic radius is to be computed for this. How do you calculate this hydraulic radius? By definition, hydraulic radius R is equal to the wetted area divided by wetted perimeter. Wetted area A is to be calculated first. So wetted area, also called the cross-sectional area of the flow section. So A would be equal to, for a rectangular channel, bed width multiplied by the depth of flow. Bed width is given to be 2.5 meters. The depth of flow is 1.2 meters. So 2.5 multiplied by 1.2. Then the wetted perimeter. Wetted perimeter P would be the length of the channel boundary in contact with the flow. So for a rectangular channel, the bed width B in contact with the flow, and the depth of flow on one side, the depth of flow on the other side. Both the sides of the section is in contact with the flow. In contact with flow. Just take back 1 second to the figure. How do you calculate the wetted perimeter? The wetted perimeter is the length of the channel boundary in contact with the flow. So for a rectangular channel, the flow may be taking place like this. So what is the channel boundary in contact? So starting from this point, all this bed width, all this depth of flow Y, the bed width B, and the depth of flow Y is in contact with the channel boundary. So Y plus B plus Y would be equal to B plus 2Y is the wetted perimeter. B plus 2Y is the wetted perimeter. B, the bed width, 2.5 meters. 2.5 meters. Y, the depth of flow. So 2 into 1.2 meter. You got now the wetted perimeter. Cross-section area or wetted area, wetted perimeter. By definition, wetted area divided by wetted perimeter is hydraulic radius. So hydraulic radius R is equal to A by P. Wetted area 3 square meters divided by hydraulic radius 4.9 meters. So 0.612. Hydraulic radius has come down. Now after calculating the hydraulic radius, now you got the unit weight of water, longitudinal slope, both are given in the problem itself. A simple substitution. Gamma, unit weight of water, 9810 Newton per meter cube into hydraulic radius or 0.612, just now we have computed, multiplied by S0 to the longitudinal slope 0.0036. So substituting that, you got 21.58 pascals is the average momentary shear stress. Second problem, a trapezoidal channel has a bed width of 2 meters. Earlier we have taken up rectangular channel, now we are now talking about the trapezoidal channel. So the trapezoidal channel having a bed width of 2 meters, side slope 1.5 horizontal to 1 vertical. Z is given. Okay, 1.5 horizontal to 1 vertical. Then the channel has a longitudinal slope of 1 by 4,000. Please note in the earlier problem, the longitudinal slope is given directly in terms of the decimal 0.0036. In this problem, it is given like a gradient 1 in 4,000. So 1 by a fraction, 1 by 4,000. And if the Manning's coefficient of the channel boundary is given to be 0.018, calculate the mean velocity and the discharge in the channel for a depth of 1.4 meters. Please try to understand the problem so that the working would be very, very simple. It is a trapezoidal channel, first point. It is a trapezoidal channel. See, the shape may be something like this, a trapezoidal channel. And this is the bottom width or bed width. Jet horizontal to 1 vertical is given here, 1.5 horizontal to 1 vertical. Okay, the side slopes of the channel is given to be jet horizontal to 1 vertical. So it is given in the problem as 1.5 horizontal to 1 vertical. So the value of z is equal to 1.5. And y is the depth of a flow. Y is the depth of a flow. So in the problem, the depth of flow is given to be equal to 1.4 meters. So y is 1.4 meters. It is a trapezoidal channel. Bed width is 2 meters. Side slopes are 1.5 horizontal to 1 vertical. Longitudinal slope is 1 by 4,000. And further, one more thing is given in the problem. The Manning's coefficient of the channel boundary is 0.018. The moment Manning's coefficient is given, it is understood that you have to make use of Manning's formula. It is implied. It is implied that you have to make use of the Manning's formula. Calculate the mean velocity and discharge. So mean velocity, how do you compute? Making use of the Manning's formula, 1 by n, r power 2/3, s power half. The discharge will be area multiplied by velocity. Area multiplied by velocity. Okay, so this is a trapezoidal channel section. Bed width B is 2 meters. Longitudinal slope S is 1 by 4,000. And the Manning's coefficient N is 0.018. These are the things given. Side slope 1.5 horizontal to 1 vertical. So Z is 1.5. Further, the depth of flow Y is given to be 1.4 meters. Y is 1.4 meters. You need to calculate the mean velocity as well as the discharge. So calculate the wetted area. Area of the flow section, capital A, is also called wetted area. Since it is a trapezoidal channel section, central rectangular portion plus side two triangular portions. So central rectangular portion B bandwidth B multiplied by the depth of flow Y plus side two triangular portions half of base into height. Half of base into height, and you need to add two times because it is on both the sides. So it is B plus half of ZY square, BY plus half ZY square plus half ZY square. B plus ZY into Y. Substitute all the values. B 2.0 meters bed width, Z 1.5, Y the depth of flow 1.4. So 2.0 plus 1.5 into 1.4 multiplied by Y 1.4. You got now the wetted area capital A. Then wetted perimeter. So wetted perimeter by definition is the length of the channel boundary in contact with the flow. Just I'll take back 1 second to the figure. Length of the channel boundary in contact with the flow. So here the top atmosphere, the free surface is that open atmosphere. It is not in contact with the boundary. But what is the portion in contact with the boundary? The channel bed plus inclined portion on this side plus the inclined portion on this side. Okay, so this is the wetted perimeter. So B at the bottom, the bed width B plus this inclined portion. How do you get this inclined portion? For one vertical, Z is the horizontal. So for Y vertical, ZY is the horizontal this side. Similarly, the horizontal component this side will be ZY. ZY and ZY is there. The base is ZY, height is Y. So what would be this portion? Square root of Y square plus Z square Y square. On both the sides, so multiplied by 2. Multiplied by 2. So you got B plus the bottom width B plus 2Y square root of 1 plus Z square. So in calculating the wetted perimeter, we have the bed width B given to be 2 meters, the depth of flow Y given to be 1.4 meters, and Z the side slope 1.5 horizontal to 1 vertical. Substitute all the values here. 2.0 plus 2 into 1.4 into square root of 1 plus Z square. Z is 1.5 square. So you have got now wetted perimeter. So wetted area has been computed, wetted perimeter has been computed. Hence the hydraulic radius R will be equal to A by P, 5.74 divided by 7.048, 0.8 meters is the hydraulic radius. Once you get the hydraulic radius, since Banach's coefficient is given in the problem, compute the velocity basing on the Manning's equation. So mean velocity by Manning's formula V is equal to 1 by N, R to the power 2/3, S power half. V is equal to 1 by N. N is 0.018 into R 0.814 to the power 2/3 into S 1 by 4000 to the power half. Substituting that, you got the mean velocity V. Once you get the mean velocity V, the discharge Q will be equal to area into velocity. The discharge equation Q is equal to A into V. Area is already computed, wetted area 5.74 multiplied by the mean velocity 0.766 meter per second. So you are getting 4.4 meter cube per second is the discharge. Third problem. A trapezoidal channel has a bed width of 10 meters and a side slope of 1.5 horizontal to 1 vertical. So what is that is given till now? It is a trapezoidal channel. This is point number 1. Okay. And bed width is given to be 10 meters. B is 10 meters. Side slopes are once again 1.5 horizontal to 1 vertical. So Z is 1.5. Manning's N can be taken as 0.015. That also is known. N is equal to 0.015. What bottom slope is necessary to pass 100 cubics of discharge in this channel at a depth of 3 meters? The depth of flow Y is given to be 3 meters. In the earlier problem, we were asked to compute the mean velocity and the discharge. But in this case, the discharge is given to be 100 meter cube per second. And we are asked now to compute what? The bottom slope. S is required to be computed. Once again, same formula. V is equal to 1 by N, R power 2/3, S power half. Or the discharge Q is equal to area into velocity. Substitute for velocity there and try to evaluate all the parameters and substitute in the equation. Try to evaluate all the parameters and substitute in this equation. To evaluate the parameters like wetted area, wetted perimeter, hydraulic radius, etc., this data is given. The data given is the bed width is 10 meters. It is a trapezoidal channel section. Side slopes are 1.5 horizontal to 1 vertical. And Manning's coefficient is 0.015. Discharge is 100 meter cube per second. Depth of flow is 3 meters. All this data is given in the problem. Trapezoidal channel section. Bed width 10 meters. And side slopes 1.5 horizontal to 1 vertical. N is 0.015. The discharge Q is 100 meter cube per second. Depth of flow Y is 3 meters. What bottom slope is necessary? That means what should be the value of longitudinal slope? Yes. S is how much. This is what is required to be found. So we have the equation for the Manning's equation like V is equal to 1 by N R power 2/3 S power half. R power 2/3 S power half. The discharge Q, the discharge equation will be area into velocity. Area into velocity. So the discharge Q is equal to area A into the velocity. Velocity is 1 by N R power 2/3 S power half. In this case, what is required to be found now? Q is given 100 meter cube per second. Yes, required to be found. Required to be found. N is also given 0. How much it is given? 0.015. So what are the other parameters? Wetted area you have to compute, wetted perimeter you have to compute, and then hydraulic radius you have to compute. Substituting that, you will be able to get the value of the longitudinal slope. Yes. So area of the flow section, wetted area, capital A is equal to B plus Z by into Y, trapezoidal channel section. B, the bed width 10 meters plus Z is side slope 1.5 into the depth of flow 3. You are getting 43.5 square meters as the wetted area. Wetted perimeter P will be equal to B plus 2Y square root of 1 plus Z square. B 10 meters into 2 into 3 into square root of 1 plus 1.5 square. 20.817 meters. Wetted perimeter has been computed. Wetted area has been computed. Next what? Next is hydraulic radius. Hydraulic radius would be equal to A by P. A by P. Hydraulic radius R would be equal to A by P, and you got 2.09 meters. Then the discharge Q, and substitute all these values what you have obtained. 1 by N, A, R power 2/3, S power half. Q is 100. 1 by N is 0.015 into wetted area A, area of the flow section 43.5 into R to the power 2/3, R is 2.09 to the power 2/3 into S to the power half. Solve for S. Say one equation, one unknown. So the value of S may be expressed in terms of a fraction or like a decimal 0.0004449796 or 1 by 2247. Next problem. For a flow in a rectangular channel of width 5 meters and depth of flow 2.3 meters, the Darcy-Weisbach friction factor is estimated to be 0.02. Estimate the value of the Chezy's coefficient and the value of the Manning's coefficient. This problem is slightly different from the earlier two problems. In the earlier two problems, what we have done, let it be a rectangular channel, let it be a trapezoidal channel, we were attempting to compute the value of either velocity or discharge or longitudinal slope given the other parameters. But in this case, Darcy-Weisbach friction factor is given, and you are required to estimate the value of the Chezy's coefficient C and the Manning's coefficient N. We know Chezy's formula, we know Manning's formula, we know Darcy-Weisbach formulas. So we try to compare or equate these things so that we will be able to arrive at the required coefficients. We know the Chezy's formula, V is equal to C into square root of R into S. C is the Chezy's coefficient, R is the hydraulic radius, S is the longitudinal slope. Similarly, Manning's formula, 1 by N, V is equal to 1 by N, R to the power 2/3 S power half. R to the power 2/3 S power half. Then Darcy-Weisbach, the velocity V is equal to square root of 8G by F into square root of RS. Okay, so don't bother about this S naught, S, and the difference, both are same. As far as the uniform flow is concerned, both are same, no need to worry. Take S naught equal to S. Okay, then if you start comparing and trying to substitute the values, V is equal to 1 by N, R power 2/3 S power half. Manning's formula, V is equal to 1 by N, R power 2/3 S power half. 1 by N into R to the power 1/6 into R to the power half. What I have done now here, I have changed it. This R to the power 2/3 has been changed into R to the power 1/6 into R to the power half. R to the power half. The reason is when I convert this into R to the power half and R to the power S, it becomes square root of RS. It becomes square root of RS. So R to the power 1/6 into R to the power 1/4, 1/2 becomes something like it becomes how much? 6 plus 2 divided by 12 or 2/3. 2 by 8 by 12 or 2/3. So the velocity V would be equal to 1 by N into R to the power 1/6 into square root of RS. 1 by N into R to the power 1/6 into square root of RS. Square root of RS. So if we just compare this, with this, the value of C would be equal to 1 by N R to the power 1/6. Comparing, the value of C would be equal to square root of 8G by F, also would be equal to 1 by N R to the power 1/6. So for the given problem, it is a rectangular channel. Bandwidth is given to be 5 meters. Depth of flow is 2.3 meters. Friction factor is 0.02. So hydraulic radius R would be equal to A by P. Wetted area divided by wetted perimeter. Wetted area B into Y. Wetted perimeter B plus 2Y because it's rectangular. So B is 5 into Y is 2.3. 5 into 2.3 by 5 plus 2 into 2.3. 1.19 meters is the hydraulic radius. So C will be equal to square root of 8G by F, 8 into 9.81 divided by 0.02, which is given already. So substituting that, you are getting the Chezy's coefficient to be equal to about 62. Please note, it is coming to about 62. Whereas Darcy-Weisberg friction factor is of the order of usual range is 0.02. And what is the Manning's coefficient range that we have seen? 0.015, 0.018, 0.02, like that. Okay, we have seen in the problem. So this range also is very, very important. Further, you may notice that these ranges are applicable only when you are using this MK system of units. From one unit system to the other unit system, these values also would be changing because these equations, let it be Chezy's formula, let it be Manning's formula, these are semi-empirical formulae which are not dimensionally homogeneous. So that is why the normal range of the coefficient of value is directly linked with what type of unit system that you are using. So for this system, the value of C is about 62. So C is 62.64, which is equal to 1 by n r power 16. Just now we have compared. So Chezy's coefficient C is expressed to be in terms of the Manning's coefficient as 1 by n r to the power 16. Just with the previous comparison we have got. So substituting that, C is equal to 62.64 is equal to 1 by n r to the power 16. 1 by n r to the power 16. And hence 1 by n would be equal to 62.64 divided by r to the power 16. Substituting the value of n is 0.016 in this case. Okay, in the previous two problems we have got 0.02, 0.015, 0.018. Now it is 0.016. This is the usual range of the Manning's coefficient. Okay. So n value 0.016, Chezy's coefficient 62.64, and friction factor is given to be 0.02 already. Okay. So this is the problem. In this problem is slightly different from the earlier problems. In the earlier problems, it may be a rectangular channel or it may be a trapezoidal channel where you are asked to find either the longitudinal slope or velocity or the discharge given all other geometric properties of the section. But in this case, given the geometric properties of the sections, you are required to find the coefficients like Chezy's coefficient, Manning's coefficient, etc. Next problem. A trapezoidal channel has a bed width of 3 meters, side slope of 1:1. So once again, the details are given. Bed slope 0.0036. Three things are given here. Trapezoidal channel, point number 1. Bed width 3 meters, B is equal to 3. Side slope C is 1:1, so Z is equal to 1. And then longitudinal slope, bed slope is given to be 0.0036. S is given 0.0036. The discharge Q is 15 meter cube per second passes in this channel at a depth of 1.25 meters. So the depth of flow Y also is given. Estimate the Chezy's coefficient C. So make use of Chezy's formula. B is equal to C into square root of RS, square root of RS. So to make use of this Chezy's formula and to get the value of C, what is required? On the left hand side, you have the velocity V. But in the problem, the discharge is given. The discharge is given. So you can directly make use of the discharge equation. Q is equal to A into V. Q is equal to A into V. So you have a trapezoidal channel, bed width 3 meters, side slopes 1:1, longitudinal slope 0.0036, discharge 15 meter cube per second, depth of flow 1.25. All the parameters required are given. Since it is a trapezoidal channel, the wetted area A is equal to B plus ZY into Y. Substitute the values. B, bed width 3 meters, Z is 1, and Y is 1.25 depth of flow. You got 5.3 square meters. Wetted perimeter P is equal to B plus 2Y square root 1 plus Z square. So substituting those values, the value of P, wetted perimeter 6.5 meters. Wetted area is computed, wetted perimeter is computed. Next what? Hydraulic radius. Hydraulic radius is A by P, 5.3 divided by 6.5. 0.8 meters is the hydraulic radius. Once you get the hydraulic radius, Using the Chezy's formula, the discharge equation Q is equal to area into V, the velocity V is equal to C into square root of RS. C into square root of RS. So the discharge Q is equal to C into A into square root of RS. C, Chezy's coefficient, which is required to be found. Q, the discharge, given to be 15 cubics in this problem. Vector area, we have computed 5.3, hydraulic radius 0.8, and longitudinal slope is given 0.0036. Substituting all the values, the Chezy's coefficient C, you obtain 52.1. Just make note, in the earlier case, you got 62 as the Chezy's coefficient. For this problem, you got 52 as the Chezy's coefficient, which indicates that the general range of the Chezy's coefficient would be of the order of 50 or 60. Okay, when you are using MK system of units. Similarly, the general range of the Manning's coefficient would be 0.015, 0.018, and so on. That is the general range. Next problem. What size of a circular drainage pipe is needed to carry 1.1 meter cube per second of discharge when flowing half full? I repeat once again this first sentence. What size of circular drainage pipe is needed? So you need to estimate the size of the pipe. This is number one. Number two, what is the shape? It is circular. So the channel section just now we have seen trapezoidal. In the earlier case we have seen rectangular, but now it is given a circular drainage pipe. It is a circular drainage pipe. You may get a small doubt at this point that when I say circular pipe, naturally it becomes a pipe flow. How can it be analyzed in open channels? You may get a doubt that how this problem can be analyzed in open channels. This would be treated as open channel provided there is a free surface. If it is not having a free surface, then what will happen? Entire cross-section area will be completely filled with the flowing fluid. Then it will be treated as pipe flow. It will be treated as pipe flow. If the pipe is flowing half full, that means the entire cross section is not completely filled with the flowing fluid. It is only half full, which indicates that it is having a free surface. The moment there is a free surface, then automatically the flow will be categorized as open channel flow. Only for the sake of convenience, it is taken like a circular conduit. It is taken like a circular conduit. So what size of the circular drainage pipe is needed to carry 1.1 cubic meter per second of discharge when flowing half full? The pipe is laid at a slope of 0.0004 and the Manning's coefficient N is 0.018. The moment Manning's coefficient is given, we may need to make use of the Manning's equation. This is point number one. You may need to make use of the Manning's equation, V is equal to 1 by N R power 2/3 S power half. Second thing that is given is that though it is a pipe, though it is a drainage pipe, it is not running full. It is not running full. So there will be a free surface. Once there is a free surface, this is considered to be open channel flow. So the applicable governing equations would be either Chezy's formula or the Manning's formula. So the discharge given to be 1.1 meter cube per second. Longitudinal slope is given to be 0.0004 and Manning's N is 0.018, and let D be the diameter of the whole pipe. And why the depth of flow in the problem it is shown like it is running half full. I have taken only a typical circular channel section. If a typical circular channel section, the depth of flow Y would be considered to be from the free surface to the bottommost point. From the free surface to the bottommost point. But for this problem, where is this free surface? The free surface is exactly at the center. It is running half full. This entire full pipe, it is half of this pipe. That means up to this portion, the water is flowing, the drainage is flowing. So the depth of flow would be equal to Y would be equal to half of the diameter. So the depth of flow Y is D by 2. Wetted area would be equal to half of pi by 4 d square, because you need to take wetted area. It is the cross-sectional area of the flow section. You should not consider the entire cross-sectional area of the pipe. It is only the cross-sectional area of the flow section. If D is the diameter, the cross-sectional area of the pipe will be pi by 4 d square. However, it is running only half full, half of it. So 1 by 2 into pi by 4 d square. or pi by 8 d square is the wetted area. And what is wetted perimeter? It is the length of the channel boundary in contact with the flow. So if you take the entire perimeter, it is pi d, but half of it only it is running. So half of pi d will be the wetted perimeter. So pi by 2 into d. Then hydraulic radius will be by definition wetted area by wetted perimeter. Pi by 8 into d square divided by pi by 2 into d. D gets cancelled and you got only d by 4. R is equal to d by 4. So using the Manning's formula, Q is equal to 1 by n, A r power 2/3 s power half. Please note that this is the Manning's formula applied in the discharge equation Q is equal to A into V. The discharge equation Q is equal to A into V. So using Manning's formula, I am writing here. It is not the Manning's formula. Manning's formula is only the velocity V is equal to 1 by n r power 2/3 s power half. Using that Manning's formula, the discharge equation Q will be equal to area into velocity, which is equal to 1 by n A r power 2/3 s power half. So substitute all the known values. The discharge Q, it is a circular drainage pipe carrying 1.1 meter cube per second of discharge. So Q is equal to 1.1 is equal to 1 by n. N is 0.018 into wetted area A pi by 8 into d square. Hydraulic radius r d by 4 to the power 2/3 into the longitudinal slope given to be 0.0004. So substituting these values in this equation, you have only one unknown, capital D. That is the size, the diameter of the pipe. Solve for this unknown, one unknown and one equation. So value of D is equal to 2 meters. Value of D, the size of the pipe is 2 meters. Next, a rectangular channel 3.5 meters wide is laid on a slope of 0.0005. Calculate the normal depth of flow for a discharge of 5 meter cube per second in this channel. Value of n is given to be 0.02. So this is once again a rectangular channel 3.5 meters wide, but width is 3.5 meters. Longitudinal slope is given, S is equal to 0.0005. You need to find the normal depth of flow. We are introducing a term, normal depth of flow. Till now, we have been using the term only depth of flow. Why? How do you define the depth of flow? Depth of flow is the depth measured from the free surface to the bottommost point of the channel section. Let it be a triangular section, let it be a rectangular section, let it be circular, let it be whatever may be the shape. But from the free surface to the bottommost point at a given section, that is called the depth of flow Y. Depth of flow Y. Then what is this normal depth of flow? What is this normal depth of flow? Usually, depth of flow Y is applicable for any type of flow that is taking place in the channel. However, normal depth of flow would be corresponding to the depth in the uniform flow of a channel. In you are considering a uniform flow in this channel, so normal depth of flow would be equal to the depth of flow for this case. A rectangular channel, longitudinal slope 0.0005. The discharge Q is given to be 5 Qmax. Manning's coefficient n is 0.02. And the bed width is given 3.5 meters wide. So the bed width B is 3.5 meters. And you need to compute the value of the depth of flow Y. So area of the flow section in terms of Y only, because you don't have the value of depth of flow in this problem. You don't have the value of depth of flow in this problem. The discharge also is given. So since Manning's coefficient n is given, make use of Manning's formula. Make use of Manning's formula. But Y is not there. Use Y only. In terms of Y, you try to arrive at the equations. So area of the flow section, wetted area will be equal to B into Y. 3.5 into Y. Wetted perimeter is B plus 2Y. 3.5 plus 2Y. So what is the value of hydraulic radius? A by P. Wetted area by wetted perimeter. 3.5 into Y divided by 3.5 plus 2Y. This is the hydraulic radius. I repeat once again, the rare cases also, one value is not given and we try to estimate. Maybe Chezy's coefficient has been estimated in one problem. Longitudinal slope has been calculated in another problem. Mean velocity has been calculated in one problem. Discharge is calculated in one problem for different shapes. However, the governing equations are either Chezy's equation or Manning's equation. Here also same thing, but the difference as compared to the other problems to this problem is, in this problem, the depth of flow Y is not given. So let it be Y only. Let Y be the depth of flow. Then what will be the wetted area? Wetted area is B into Y, 3.5 into Y. Wetted perimeter, B plus 2Y. That is 3.5 plus 2Y. And hence the hydraulic radius will be A by P, 3.5 into Y divided by 3.5 plus 2y is the hydraulic radius. Then the discharge equation, Q is equal to 1 by N, A, R power 2/3, S power half. So whatever is the known value, substitute. Left hand side Q, the discharge, 5 meter cube per second. So 5 is equal to 1 by N, 1 by 0.025 into area 3.5 into Y into hydraulic radius 3.5 into Y divided by 3.5 plus 2y whole to the power 2/3 into S is 0.005 to the power half. So what is not there in this equation? Small correction, first point. S in this problem is given to be 0.0005. So substitute same thing. Small mistake here, 0.0005. Then what is to be found from this equation? This is also one equation. How many variables are there? Only one variable, y. When the number of equations are equal to the number of variables, certainly you will get a unique solution. Why can we solve? Why can we solve from this equation? You may have the trial and error procedure also, because this equation is a cubic polynomial. You may make use of the trial and error procedure. I'll just try to introduce you what is this trial and error. What is this trial and error procedure? You have the equation with left hand side some value 5. Equation with right hand side involving the variable y. What you need to do is let y may be assumed some initial guess value. Y is equal to 1. That is what has been done. We have assumed y is equal to 1 meter. If y is equal to 1 meter, what is the total value of the left hand side? Left hand side there is no variable, so left hand side is ls is only y 5. Right side, substituting the value of y is equal to 1. How much you are getting? So right side is 2.89. That means left hand side is 5, right hand side is 2.89, which is not equal to left hand side. So your trial value or your assumed value is not correct. If your assumed value is correct, the left hand side must be equal to right hand side. In other words, you should continue this trial and error procedure till such time the left side value is equal to the right side value, and in such case your assumed value will be the actual depth of flow y. So I increase it to 1.5 meters in the second try. Calculate the left side, calculate the right side. It has come to 5.09. You see, very near to 5. Left side of 5, right side 5.09. When I assume a value of 1.5 meter, is coming very nearer. So it may be slightly less than 1.5. So if you try for 1.48, probably you may be getting the left hand side 5 and right hand side 4.9999, something like that. So the depth of flow y would be equal to 1.48 meters. 2 points you need to note at this juncture. Point number 1. In this trial and error procedure, you may not get exactly equal values for left hand side and right hand side. If you start trying to attempt for making the exact value on the left hand side as 5.0 and right hand side also must be equal to 5.0, probably you need to keep more number of tries, which is not required. At the end, what will happen? The depth of flow 1.48 meters would be measured. It could be 1.481. It could be 1.479 also. So no need that you should go for exact precise values for equating left hand side to right hand side. If it is approximately nearer, you can stop that procedure there. Second point is the same equation can be solved as a cubic polynomial making use of your calculators also. Third point, which is very important, is in the trial and error, what is the initial guess that you are making is very important. In this case, in this particular problem, I assumed the value of y, initial value to be equal to 1. Then I got 5 and 2.89 coming to around 3, 5 and 3. So I thought that it should be little more to reach this 5. So immediately I got for 1.5. So your initial guess is very, very important. Suppose if I make use of the initial guess to be equal to 0.1 instead of 1.0. Can you imagine where do we land up and when do we finish this problem? It takes a number of iterations. number of iterations. So initial guess is very, very important, for which you should have certain physical idea about the problem. Physical idea about the problem. That means you need to carry 5 meter cube per second of water in a canal, in a channel. What should be the usual depth of flow? Maybe 1 meter or 10 meters. That is very, very important. Instead of keeping 1, if you keep 0.1, convergence is very difficult. If you keep 10 also, convergence is very, very difficult. So that is how initial guess is very important for the trial and error procedures. Next, a circular drainage pipe 0.8 meters in diameter conveys a discharge at a depth of 0.3 meters. If the pipe is laid on a slope of 1 in 900, estimate the discharge n 0.015. Look at this problem. Once again, this problem is related to a circular drainage pipe. Usually, we make use of the circular drainage pipes in our colonies, right? In any of the colonies, the drainage pipes usually would be circular in nature, through which the water may be, the rainwater or the drainage water may be flowing. So, it is a circular drainage pipe. The diameter is given to be 0.8 meters. In the earlier problem, we have got the diameter to be equal to 2 meters. We have computed it as 2 meters. In this problem, it is 0.8 meter. It conveys a discharge at a depth of 0.3 meters. It is not running off full. Unlike earlier problem, it is now having a depth of flow y to be equal to 0.3 meters. 0.3 meters. If the diameter is 0.8, what is the radius? 0.4. So up to half full, it should be 0.4, but the depth of flow is 0.3, slightly below that. If the pipe is laid on a slope of 1 in 900, that means longitudinal slope S is given to be equal to 1 by 900. Estimate the discharge. Take the Manning's value, Manning's coefficient n 0.015. So in the problem, you can see AB is the top width. AB is the top width for this open channel section. Of course, the shape of the channel section is circular. AB is the top width of the free surface. Sorry. AB is the top width of the free surface. C is the center of the circular drain pipe. CD is the radius of the circular pipe, which is equal to small r. CD is the radius of the circular pipe, which is equal to small r. What is DD dash? DD dash is the depth of flow y. And CD dash is the height of the apex in this triangular portion. If you see, ABC is a triangular portion. So in this triangular portion, with respect to the base AB, C is the height of the apex. So CD dash is the height of the apex. Of course, theta, the inclined angle. Theta is the inclined angle. What is required now is you have to calculate the discharge Q. You have to calculate the discharge Q. So to calculate the discharge Q, since Manning's coefficient n is given, we make use of the Manning's formula. V is equal to 1 by n, r power 2/3 s power half, and use the discharge equation. Q is equal to area into velocity. So Q will be equal to 1 by n, A, r power 2/3 s power half. S is given, n is also given. So two more variables are to be found. One is hydraulic radius and the other is wetted area. So you need to compute the wetted area of this circular portion. Wetted area of the circular portion will be ADBA. ADBA is the wetted area, cross-sectional area of the flow section. So to get this cross-sectional area of the flow section, ADBA, what we try to make use, we make use of the trigonometry. We calculate the cross-sectional area of the arc subtended with an included angle of theta. That means area CADBC minus area of the triangle CAB. Area of the triangle CAB. Then you will be getting the wetted area A. Wetted area A. Okay. So the details are given. Diameter is given. Depth of flow is given. Manning's n is given. And the longitudinal slope is given. And you are expected to compute the discharge Q. CB in the problem is 0.4 meters because it is the radius. CD dash is 0.4 minus the depth of flow 0.3, 0.1 meter. 0.1 meter. So take cos theta by 2 and hence the value of theta which is taken in radius is 1.31. So that what I am doing using simple trigonometric principle, cos theta by 2 would be equal to CD dash by CB. CD dash by CB. So you will be getting the value of theta from there. Theta is 1.318 radians. Once you get the value of theta, you'll be able to compute what is the top width. The top width is AB. In the figure, top width is AB, which is equal to AD dash plus D dash B. AD dash plus D dash B will be the top width. Since the included angle in the half triangle is theta by 2 and CB is the radius R, so this becomes R cos theta by 2, this becomes R sin theta by 2. So you have the top width to be twice of R sin theta by 2. So R sin theta by 2 plus R sin theta by 2, it will be 2R sin theta by 2. Similarly, the vertical intercept CD dash would be R cos theta by 2, height of the apex. Then vectored area will be area CADBC minus area of the triangle CAB at the top. So theta by 2 pi, the included angle theta divided by 2 pi into pi r square minus area of the triangle. Area of the triangle, half of base into height. Half of base 2R sin theta by 2 into height R cos theta by 2. So on simplification, R square by 2 into theta minus sin theta is the vectored area. Similarly, the vectored perimeter is the length of the channel boundary in contact with the flow. That is the length of this arc subtended, the length of the arc subtended with the included angle theta, which is equal to R into theta. R into theta. So vectored area, vectored perimeter are known, and hence the hydraulic radius R can be computed. Substitute the values. Vectored area A would be equal to R square by 2 theta minus sin theta. R is 0.4. So 0.4 square by 2 into theta minus sin theta, 1.17 meters square. And vectored perimeter is R into theta. Please note that the theta value is substituted in radians in both the cases. 1.055 meters. Then hydraulic radius is A by P. The discharge Q is equal to 1 by N, A, R power 2/3, S power half. So substituting those values, you are getting the discharge Q 0.1143 meter cube per second. So this finishes the working of some of the problems. We try to analyze the uniform flow with the different shaped channel sections like rectangular shaped channel section, trapezoidal shaped channel section, or a circular shaped channel section by making use of either Chezy's formula or Manning's formula and various varieties of problems that we have taken, calculating the longitudinal slope in one problem, calculating the mean velocity, calculating the discharge, calculating the depth of flow by making use of the trial and error procedure, etc. So we try to cover all varieties of the problems in application of the uniform flow in open channels. So this is what is the analysis of the uniform flow in open channels. I request all of you, please work out these problems once again.